Welcome to the course Business Analytics and Data Mining Modeling using R. In the previous lecture, we were discussing performance metrics. So, we were discussing asymmetric misclassification cost. So, we will pick up our discussion from there. So, as we were talking about the asymmetric misclassification cost and how it can be important in a business context, right. So, let us open the Excel file so that we are able to recall some of the thoughts that we had in the previous lecture. So, we talked about this particular example where the sample size is 1000 and we have 1% buyer, others being non-buyers. We talked about what will happen in a new classifier case, and we will have 1% of error if we classify all the records as non-buyers. Therefore, 1% buyers would also be classified as non-buyers and will have 1% error. We also have hypothetical data mining model where the results would be in this form of this classification matrix, where we have this prediction that 970 members classified correctly as class 0 members, and 8 members classified correctly as class 1 members, others are misclassification errors. So, that would lead us to 20 plus 2, that off diagonal elements, and 2.2% error. So, we talked about that despite being more misclassification error, higher misclassification error, this particular data mining model could be preferable to us because of the profits that would be involved, the value that we can get from a customer selling a particular item to the customer. So, that also we saw through this example where we had this matrix of our profit when the focus is on the profits, and then we also had this matrix of cost. So, we have gone through this. So, in matrix of profit we saw that through this example exercise that 60 rupees profit we could make per buyer, and then we through a matrix of cost, this is 60 rupee profit is from all the from the whole data mining exercise from all the buyers. Then we had matrix of cost. From the cost perspective we had $40 to $8. So, our purpose is going to be, when we take profit and cost into account, the purpose is going to be maximization of profit or minimization of cost. But if we look at the improvement in our classification model, so we won't see much in using these ways. So, therefore, we talked about another performance metric that was average misclassification cost. So, this was the formula where we take, so this particular average misclassification cost, as we talked about, measures average cost of misclassification per observation, and this is the formula that we also discussed in the previous lecture, right. So, we also talked about that this particular, we look at this particular formula, the values n01, n10, n being can be considered constant, and therefore, the minimization of this quantity that we require would essentially be based on the ratio of C0 and C1, right. So, we would essentially be, and it would be easier for us to estimate the ratio of C0 and C1, right, cost of misclassifying a class 0 observation or class 1 observation, right. It would be easier for us to estimate that, and therefore, essentially the software which will try to minimize this particular expression average misclassification cost would essentially be doing on the basis of this particular ratio. We also talked about, that is why many commercial statistical software, they will ask you to specify if there are any misclassification cost. We also talked about that some software will also ask you to specify if there are any prior probabilities. So, that was the discussion that we were having. So, why we would be requiring prior probabilities in the first place. So, sometimes it might happen that the model, we are building our model on a particular training partition, and the ratio of different classes might not remain same when we apply our model on new data. So, the ratio of class 0 members and to class 1 members, or number of class 0 members and number of class 1 members, that proportion might not be same in the new data or in the sample data. So, if while we are building our model and the sample that we are going to use to build our model, and that sample might not have the proportion of class 0 members to class 1 members as would be there in the real data, in the actual data that would also be used for testing, then we might incorporate that in our modeling process. So, how we incorporate that? By specifying the prior probabilities. So, that is P0 and P1, P0 for class 0 members and P1 for class 1 members. So, even in this case also we would be just taking the ratio of these two prior probabilities would suffice us to minimize this minimize the expression. So, we would essentially be minimizing P0 divided by P1 and C0 divided by C1. So, this is the expression that would essentially be minimized by the softwares instead of the full expression. Now, we also talked about previously the importance of lift curve and how it can be used to understand, to evaluate the effectiveness of a model. We saw that in comparison to a random selection case, how the lift curve can tell us about the lift that we will get for a particular model as the number of cases increase, right. So, we saw that through this decile chart also. Can we generate a lift curve while incorporating cost? So, let us do an exercise where we do this. So, let us open RStudio. So, as usual we will first load this particular library. Data set that we are going to use is particular again is in the same sheet cutoff data.xlsx. So, now let us have a look at the data as well. So, the data set that we are going to use is this one. So, you would see that 5 variables are there, but if you look at these are based on the results. So, we have serial number that representing the index of a particular observation, and the data has been sorted based on the estimated probabilities of class membership, specifically class 1. So, based on the estimated probability of class 1, the data has been sorted. You can also see then that actual class in the third column has also been mentioned. So, that particular observation belonging to the actual class of that particular observation, and the probability of class 1 is given there. So, 0.5 if any probability value being more than 0.5. So, that class would be predicted as the 1, otherwise 0. So, now in this particular data set you can also see that we are trying to incorporate the cost, the concept misclassification cost concept that we discussed. You can see here cost of sending the offer we have specified as 1 rupee, and value of a buyer that we have specified as 10 rupee. So, now at this point I would also like to tell you that this is a small data set. So, the plot that we are going to generate would be slightly different in comparison to if we had full data set, bigger data set. So, from this example you would also know that there are 12 ones and 12 class 0 members and 12 class 1 members in this particular small data set. Now, depending on the actual class I have specified, you can look at the Excel formula that is there. Depending on the actual class I have specified the cost. So, that is if the actual class is 1, then value of a buyer that is 10 rupees that would be taken up. If it is 0, then the cost of sending the offer that would be used. Once this value is there, then we can also find out the cumulative cost. You can see the cumulative cost here. So, to compute the cumulative cost for each observation, for the first observation it is going to be the same as cost for the next observation. We are going to add the value of previous result as well. So, in this fashion we will continue, and up to the last observation. So, we will have this. So, essentially in the lift curve we would be plotting this number, cumulative cost number, with respect to the index of the observation. So, let us open RStudio. So, you would see there is slight change in the function read.xlx that we are going to use. Here you would see that I have taken the this seat index as 5, this is 5th worksheet, and you would see also that column index another argument I have used. So, we just want to import the data of first 5 columns. So, that is starting from 1 to 5. So, only these. So, we are interested in importing only this data, right. Other details, this particular detail, cost of sending the offer and value of buyer, this we do not want to include in our imported data set. So, let us execute this line and we will get the appropriate data set into our environment. So, let us look at the data that we are going to use for this lift curve generation. So, we have 5 columns here, serial number, that is representing the index of the observation, and then the probability of class 1. So, this is so this particular data set has been sorted from higher probability to lower probability, the estimated probability by the model. Small data set, we have 24 observation, and we have 12 observations belonging to class 1 and 12 observations belonging to class 0. The we have third column is also mentioning the actual class of particular observation, and then we have cost, which is determined by so we have some numbers here. You can see that cost of sending the offer that we have specified is 1 rupee, and value of a particular buyer is 10 rupees. So, therefore, if the offer is accepted by buyer, so the net value that we that the organization gets from a buyer is rupees 10, and if that offer is not accepted by the buyer, then it would cost them 1 rupee. The cost, this is actually the cost of sending the offer. So, you can look at the Excel formula has been appropriately specified, where if the actual class is 1, right, in that case the value of buyer 10 is mentioned. This is net value, so that is mentioned. If the class is 0, then you can see then in the other, in that case the this particular value minus of this value is actually mentioned. So, in this fashion, for every observation which has been sorted by the estimated probability of belonging to class 1, we can mention the cost. So, these particular numbers in this particular column cost, they are including the net value from a buyer or and cost of sending the offer as well. Now, cumulative cost has been computed using this particular cost column. So, in this case, first observation, the cumulative cost is the same as the cost for the first buyer. Then for the second buyer, we are adding up the cost that incurred in the first buyer. So, in this fashion, for previous cost is being accumulated and we get this variable cumulative cost. So, let us import this particular data in the R environment. So, you can see some changes in the function read.xlx that I am calling here. You can see that the worksheet that we are calling is 5. You can see in the Excel file that this is worksheet number 5, right. You can see this worksheet number file. Otherwise, you can also import the data from this worksheet by using the name of this worksheet which we have provided here as well. So, right now we are going to use the index. Then you can also see the columns that we want to import. So, we want to import column number 1 to 5. So, we are using column index argument here. You can see we are interested in column 1 to 5. This particular information we do not need for plotting lift curve. So, let us import this particular data set. You can see 24 observation of 5 variables. Let us remove if there are any columns. Let us look at the first 6 observations. You can look at the first 6 observations. Cumulative cost is there. Now, we are going to generate a scatter plot between these two variables, the serial number and the cumulative cost. So, let us look at the range of these two variables. can see that range is 10 and 112 for cumulative cost, and for serial number, as we know that there are 24 observations. So, you can see that these limits have been appropriately specified from 0 to 25 and also from 5 to 140. So, all the values would be covered in this particular range. So, let us create this scatter plot. You can see this plot. Let us zoom in. Let us also generate the reference line. So, in this case reference line is connecting the initial point, that is in this case for reference line we have taken as 0 0 and the last point, that is 24th observation, and the corresponding value. So, in this case the corresponding value is, let us confirm using Excel file, it is 108. Let us generate this line as well and legend. Now, let us look at the zoomed plot. Now, if we look at this particular plot, so this is essentially plotting the cumulative cost in the y axis and the number of cases in the x axis. So, a dotted line being the reference line, which is connecting the 0 0 to the last point. You can see the cumulative cost is continuously increasing as the number of cases increase from as we move along the x axis from left to right, but you would see at the end of it there is slight dip. The same thing is reflected in the Excel sheet that we see. You can see here that the maximum value that we have is 112, and after that you would see there is a dip, and the last value is 108. If we had a much larger data set, many more observations, this particular dip would have been even more, to the extent that this line might come down, the slope of this line might come down much more, and it can even be negative. For example, if we consider a case where we have, let us say 20,000 observations, and there the most probable ones would be selected in the initial part of the plot, and the bias, the non-bias would come later, and thereby they will decrease the last value of the last point, and the whole plot might go below the x-axis. Some part of the plot might go go below the x-axis, and therefore the slope of this reference line might even become negative. So, it can come down. So, you can see the optimal point is this particular point where the value is maximum, which is 112. This is point. This is 20th observation. So, this is where we are getting the optimal value. So, let us go back to our discussion. So, that was the lift curve. So, lift curve can actually be used to find out the most probable ones, the rank ordering, and how many probable ones can actually be send the offers first, and what is the optimal point, how many buyers should actually be sending the offer. So, from the business context, that would be more desirable. Now, lift curve that we just plotted. So, there could be two scenarios. So, one is the plot that we just generated was lift versus number of records. So, the goal was to identify see the cumulative cost that could be there, the optimal point, that where the optimal point could be, and also to identify the more likely buyers which are more likely to accept the offer. Now, we can also generate a lift curve versus cutoff value. So, if we are interested in finding out the cutoff value where the model is going to perform better, so that can also be done. So, we can also have, so depending on the goal, whether we are looking to find the suitable cutoff value, or whether we are looking to identify check the effectiveness of the model and the number of records, most probable records. So, depending on that, we can plot the lift curve accordingly. Now, whatever discussion that we had about the asymmetric misclassification cost and other concept before that, that was mainly applicable in two class scenarios, class 0 and class 1, where class 1 was our class of interest, right. Can this, all these concepts, can they be extended to M class scenario? So, if we extend asymmetric misclassification cost for M class scenario, that is M greater than true, we will have a classification matrix M class 1, M rows and M columns. So, this is going to be a much bigger classification matrix. Therefore, the kind of computations and discussions that we had, they would become even more complicated. So, we will have to deal with M prior probabilities. If suppose that sampling is distorted and the real data in the real data and the original data, the proportion is different, then we will have to incorporate M prior probabilities. Similarly, if we look at the misclassification cost, there could be M times M minus 1 misclassification cost. The understanding different misclassification cost that could be there, that would also become slightly more complex. Lift chart that we have generated for two class case, that would also be that can also not be done in a multi class scenario until and unless we identify our rare class, the class of interest, and other classes we combine and reach to the two class scenario, only then it could be used. So, otherwise the discussions related to prior probability and misclassification cost, they can be easily extended, but when we want to execute, the things are going to be, when we want to do an actual implementation of this, it would be more complicated. Next point that we want to discuss is oversampling of rare class members. So, sometimes it might be the case that the class of interest might be having very few class members. So, it might so if we are want to create a model with very few class members, the model might not be really useful. So, in this case we would be required to do oversampling of rare class members. So, that will bring us to our discussion on simple random sampling versus stratified sampling. So, when we do simple random sampling, when we have a rare class of interest with very few class members belonging to that particular class, then simple random sampling might not give us the good enough partition to build models, right. And your training partition, if it is randomly drawn, we might not get enough number of cases belonging to class of interest, and that can impact our model, and then later on its implementation on new data. So, in such situation we will have to do oversampling, as I said, and stratified sampling is generally used for this kind of task. So, generally stratified sampling is used to perform oversampling, especially if there are such groups are present where one group is dominating and other group is very few members of other groups are present. So, what could be the different oversampling approach? So, one way could be sample more rare class observations. So, this is like equivalent of oversampling without replacement. So, the sample the data set that we have, we can sample more of the class 1 members, the class of interest, right. And so, the problems that can be faced in this, so this is more desirable approach, but there could be some practical problems that we might have to encounter. For example, lack of adequate number of rare class observation. What if in the data set itself the number of rare class observation are so few that even this sampling of more rare class observation might not yield a meaningful sample, and therefore meaningful modeling. So, those practical problems we might have to encounter. Now, ratio of cost that is also difficult to determine when we are faced in this this situation where very few members are present. This ratio of cost, this is also difficult to determine. Another approach could be replicate existing rare class observation. So, this is equivalent of oversampling with replacement. So, some of the observations that are present in our data set we can replicate, we can have copy replicates the same observation and then use that for the modeling. So, this is another approach. What analysts generally do, typical solution that is adopted by analysts is sample equal number of members from both the classes. So, what they generally do is they take 50% of the members from class 1 and 50% same number of not 50%, same number of members from both the classes and then use that for their analysis. Now, if you have done your modeling using an oversampled training partition, right, or even if it is only for the rare class, then the performance evaluation you have to adjust for that oversampling. So, when we go about is when we use our model that has been developed on a oversample partition, we will have to score this particular model, right. So, validation partition. So one approach could be score the validation partition without oversampling. So, that validation partition that does not have the oversampled cases, oversample records. So, that can be used. So, that is the easier and direct and a straightforward approach. So, build your model on oversample training partition and evaluate your model using a validation partition with the taken from the original data set. Now, the another approach could be use the oversampled validation partition and then remove the oversampling effect by adjusting weights. So, these two approaches could be there. So, the steps typical steps that are taken in rare class scenario. So, build the candidate models on training partition with 50% class 1 observations and 50% class 0 observations. We take equal numbers and validate the models with the validation partition drawn using simple random sample taken from original data set. Detailed steps. So, we will stop here and detailed step of this particular procedure we will discuss in the next lecture. Thank you.